Okay, so the next one we are going to talk about is the ohmic heating. So, ohmic heating is a technology which kind of had parallel development to aseptic processing. So, even in early 1900s, the concept of ohmic heating was kind of tested, but I think never been commercialized until later in 1980s when ohmic heating kind of commercialized. So, if you look at the history of a lot of the food processing technologies, the concepts may be known a very long time, but it takes longer time to commercially adapt the technology. Number one, there's a lot of science needs to be studied, understand. The second, food industry tend to be very conservative, so they probably have hesitation to adapt new methods until they realize it's the right thing, and then it becomes once one person step in, adapt, then there's going to be a lot more people going to follow and adapt the technology. So most of you probably use a water heater at home. So you take a heater, electrical resistance heater, put a piece of bucket with the water, and then you are heating the water with the heater. So the same concept is applicable in the case of ohmic heating. So essentially, you have two electrodes, and you're going to have a food in between, and then you are applying certain voltage. Then the current is passing through the food. The food acts as a resistor, thereby you can able to heat rapidly the food. And here the electrical energy applied is converted into heat energy, and then it also volumetrically heating their mass of the product. So, if you remember, we talked about conduction heat transfer, where the heat transfer happening out, and then this center is going to heat later. Whereas, in the case of ohmic heating, the entire mass is going to be heated when you pass the electricity. So, that is called volumetric heating. If you look at microwave, it also have a similar volumetric heating. Now, the property that allow the material to heat is called electrical conductivity. So, by adjusting the electrical conductivity of the liquid and solid, you can make the liquid heat faster or solid heat faster. So, you can be able to adjust different things. And so, you have with proper formulations, you probably do not have issues with a non-uniform heating. A lot of times when you want to ensure the food safety, you need to understand the microbiological concept, but from a processing point of view, you also make sure that you are delivering your energy much more uniformly and consistently, and I think ohmic heating can help to accomplish that. So, the concept of ohmic heating started around 1841 with Prescott Joule, and even in the early days of milk pasteurization, they were attempting to pasteurize milk with the ohmic heating. However, if you look at the literature, a lot of those data in the early 1900s disappeared from the science later, because you had World War I, World War II. So, I think the focus on some of the new developments kind of moved away, and people just stayed with the canning and traditional methods. So, the innovations kind of did not happen. Then it took 1980, a UK based company called AVP Baker Company, they reintroduced the concept of ohmic heating, and today in Europe and many other places, the ohmic heating concept is kind of adapted. Basically, the Joule's law governs the how ohmic heating happens, and I mentioned the electrical conductivity is the property of the material where it conducts the electricity. So, the heat generated within the product is given by Q, is given by I square, R, and time. Q is the energy produced in the product, I is your current passing through your product, R is the resistance of your product, and then T is how much time processing time. So, you can able to rapidly heat the product, like for example, you can increase the temperature 1 Celsius per second and so on. So, it is quite rapidly you can able to do that. So, the energy delivered can also related to traditionally mCp delta T. When you do a conventional pasteurization or sterilization, the energy delivered can be used mass times specific heat by time, whereas here you can use a different approach. And this slide just to show you kind of illustrate how the current, voltage and the resistance kind of relate to part of the Ohmic heating process. The current is trying to flow through this small restriction, and the volt is the driving force which drives the thing, whereas the resistance of the material trying to block the passage of current. So, that kind of provides an idea how the Ohmic heating functions. The temperature increase during Ohmic heating can be measured by V square, and then you have what they call product conductivity rho, and then you have area of cross section, and then distance from the electrode, the mass, and then Cp is your specific heat. So, this is kind of tells you how much temperature increase happens during Ohmic heating. So, during a traditional Ohmic heating, you are going to have multiple Ohmic heaters. So, you may have in this example 1, 2, 3, 4 Ohmic heater. So, if you look at the rest of the thing, you have a feed pump, you have a holding tube, cooling section, a septic tank, filler. You may remember you have seen all these things with the aseptic processing. Only thing different here is you are using a Ohmic heater instead of conventional tubular heater or scrape surface heat exchanger. So, the concept of aseptic processing is adapted here, just you are replacing the Ohmic with the Ohmic heater with the traditional heaters. So, why do I have so many different heaters? So, I mentioned the property of the food material which conduct the electricity is the electrical conductivity. So, what happens is when you have a food material at the initial temperature, room temperature 25 degrees Celsius, you have certain electrical conductivity value. Then you are passing electric current through it. So, it is going to warm up that material. So, increase the temperature say 50 Celsius. At 50 Celsius, the electrical conductivity value may be increased, maybe from 1.2 it may become 2. With that, it allows more passage of electricity, then you can probably increase the temperature much more rapidly. So, you go to this stage 3, and then you are going to increase the temperature further. At that higher temperature, say 75 Celsius, the electrical conductivity become higher. So, that means it is going to increase. So, that means the electrical conductivity value and the temperature, they are coupled with each other. So, the temperature increase the electrical conductivity value, it pass more current, that means it is going to increase the temperature and so on. So, this is the reason why they kind of have a controlled temperature increase. They probably have 4 heaters, so that they can modulate the temperature increase in a controlled manner. So, that maybe from here the heater 1 it may be going from 25 to 70, 70 to 90, 90 to 130, 130 to 160, 150. So, you can have a controlled temperature increase rather than what they call runaway current. So, you can suddenly rapidly increasing the temperature. So, this is just a pictures illustrating how a Ohmic heater may look like. It may look like a pasteurization equipment, but essentially you have a lot of different heaters, holding tubes and cooling heat exchangers, and then you have storage tank and so on. So, this is kind of when you do canning, you have temperature, your heating medium, the conventional product going to slowly increase the temperature like this. Whereas, with the ohmic heating, you can see that the temperature increase is slow, but as you increase the temperature, you are going to increase the electrical conductivity, then you are going to rapidly increase the heating rate, further increase the heating rate, then it just quickly rise the temperature. So, this is going to much rapidly increase the temperature, and it does not, in the case of conventional, you are going to have conduction, convection, heat transfer. So, that means the heat has to travel from out to in, it is a slow process. Whereas, in the case of ohmic, the whole volume is going to be heated. So, that means the heating is going to be much more uniform under those conditions and so on. Now, what type of electrodes people use? There are different electrodes can be used. The electrodes may be made of graphite, aluminum, stainless steel. Now, when you use different metal electrodes, you can potentially have what they call electrolysis. So, that can be potentially introduce some undesirable compounds. So, what they do is they coat the electrode, platinum electrodes with the platinum, so that you can stay inert. So, you only pass the electricity, it does not interact with the product. Otherwise, what may happen is you may pit the electrode. So, in other words, with passage of electric current with so many uses, some of the aluminum or metal particles can migrate into food, and again, which is also not desirable, because from a regulatory point of view, you have to maintain the food products free from any foreign objects, things like that. So, that is where you have to coat with the platinum electrode. And you can able to develop methods to measure how much electrode migrate into the food, so that you have to report that part of your filing process. The electrodes can be different sizes, like they can be collinear, or the electrodes can be staggered like here, or they can have parallel plates, or you can have a parallel rods. So, different configurations are possible. The passage of heater, the heat exchanger can be coaxial co-field. So, what that means is you have a tube, and then you are passing through the material here, and then you have an electrode here, so that you are going to have one field here, one field here. So, you can able to have current passing through them. So, this is suited for product with the low electrical conductivity, it carries the larger current. You can have aligned field electrodes. So, you have two electrodes, and then the product is moving here, and this is suited for product with high electrical conductivity. So, in other words, if you look at ohmic heating, the design of choice of your electrode depends on what type of product you may be processing. If you look at traditionally aseptic or canning, some of the design considerations does not limit what type of products you can process. You can product wide range of products, whereas here you may have to think through, okay, I am going to process fruits with certain electrical conductivity value. So, that means the electrodes I am going to use needs to be this design, and so on. So, there is some consideration you have to change, and then if you significantly change that electrical conductivity value, different formulation, you may have to look at different set of electrode designs. This one also just to illustrate how the voltage gradient is influenced by the voltage and the distance between the electrodes. So, you have the product here, and then two electrodes, and it has a certain gap and then certain voltage. You can change the voltage gradient by increasing the voltage. So, maybe let us say this is 30 volt, you increase here 50 volt, and then this distance is 3 centimeters, you keep the 3 centimeter, but the ratio is different. So, you can have higher voltage gradient. Or you keep the same voltage 30, and instead of distance 3, you may increase the distance, you decrease the distance to say 1.5, then also you can change the voltage gradient. So, there are a number of ways you can change these properties. The other thing you can do is you can alter the electrical conductivity of your material. By altering the electrical conductivity, also you can able to change your properties, so that you can able to get the appropriate heating rate. So, in all these cases, you are kind of trying to have certain voltage gradient in the Ohmic heater, so that you achieve certain heating rates. So, you can do that by adjusting the gap or increasing the voltage or change the properties of the your formulation. So, one limitation is how do you change the electrical conductivity of food formulation? Give you some thoughts. So, the answer is you can change that by adding or removing salt. So, salt can increase or decrease the electrical conductivity of your food material. So, you can able to do that. What that means is only so much salt you can add to your food material. So, you cannot add large amount of salt to increase the electrical conductivity, because people need to consume the food. So, if you have too much salt, that is not considered healthy, people may not perceive that as a healthy option, and so on. So, there are constraints placed to that as well. There are different companies supply Ohmic heaters. These are just to give some examples. Some of them are located in the UK, France, and then Japan, Italy, and so on and so forth. So, we already kind of talked about electrical conductivity, and we will now look at the factors affecting electrical conductivity. The electrical conductivity of the material is going to be affected by what type of salt ions you use, and what type of dissociation they have, what type of viscosity the medium you have, and how quickly the temperature increasing, cellular structures, and all those factors can affect the electrical conductivity values. The next one, we are borrowing some literature from the electrical engineering field, because now Ohmic heating is a electrical based technology. So, that means you need to have some knowledge of electrical engineering, and the reason for this is just to show how the product going to heat inside the Ohmic heater. That depends on how the product align itself within the heating medium, or they align as a resistance in series. So, that means all the particles move through in a circular row. So, there may be heat is kind of coming in, heat first, second this, third, and so on, or are they going to arrange in parallel. So, there may be particles flowing in 2 rows in ideal case, but in nature you may have random configurations. So, that means some particles may be flowing in series, some flowing in parallel, and so on. So, this is something you have to kind of make estimation. Different food materials have different electrical conductivity values. So, carat, for example, 0.041 Simon per meter. Simon is the unit for measuring the electrical conductivity. So, it kind of provides that value. Whereas, if you look at salt solution with 0.2% salt, 0.34, when I add 2% salt, it significantly increases the electrical conductivity value. So, again you can alter the electrical conductivity, you can by adding or removing salt. The other factors affecting the electrical conductivity of the material is the fouling. Remember, fouling is when you process a protein product, like for example, egg yolk or milk or any protein products you are heating, you are going to have deposits in the heat exchanger surfaces that's the fouling, and that needs to be removed. If you don't remove, it's going to reduce the heat transfer to heat exchanger surface. The same way, when you have ohmic heater, you're going to have heating electrical resistance heater here. With usage, you're going to start forming fouling, and that's going to decrease the efficiency of your electrical resistant heating. That means it's not going to pass the electricity properly, so you have to kind of again pay attention to that. The frequency of power source probably also pay attention. So the line frequency in the US is 50 or 60 hertz. So can the frequency increase to 100 hertz or 120 hertz? Those also affect the electrical conductivity values. So this slide just to illustrate what happens when you are heating potato with ohmic heating, or like in this case starch with ohmic heating. So you start at 25 degrees Celsius or 20 Celsius, you have certain low value here, and then as you warm, you can see that the conductivity increases from say 0.05 to say 0.1, then it is relatively stable from 40 to 70 Celsius. And at around 70 Celsius, you are going to gelatinize the starch, say in a potato. Then you can see that it breaks down, so then it's going to significantly increase your electrical value, say from 0.1 increases to 0.3 or 0.4. That means the heating rate may be slow here. Once the electrical conductivity starts increasing significantly, the heating rate also significantly increase much more faster. Here we kind of illustrates that you have a potato particle and how the potato is oriented with respect to the electrode. So you have electrode here, the particle here, and then the heating rates can be so the liquid is dotted line. So this is the liquid, whereas the potato is here, this is the solid. So this is when the electric field, and then this potato is kind of parallel to that, whereas here you have electric field and then the potato is horizontal, and you can see that the same potato, same condition, but you just change the orientation, the heating rates of solids and reverse under these conditions. So again, ohmic heating is kind of much more complex compared to some of the traditional canning and other methods. So that's where again you need to have mathematical modeling to understand various things happening during ohmic heating. This slide just to show the electrical conductivity of solids, like for pieces like a potato, how when you change the applied voltage from 0, there is no current passing through, to 40 volt per centimeter, like so much volt gradient is there, and you can is able to achieve under those conditions. This is showing for a liquid. So, for example, orange juice, and again at the different voltage gradients what happens. So, generally as you increase the temperature from 20 to 80 Celsius, you can see that straightforward increase. Then it's kind of dropping here, but this is more experimental artifact, because at 100 Celsius water start boiling. If you don't pressurize it, then you're going to evaporate. So, that's going to give you a different sense, false temperatures reading. So, this is where this data is not reliable. So, you have to have a pressurized electrode or system to measure the electrical conductivity at higher temperatures. So, in terms of critical process temperature conditions, temperature and time. So, what is critical process temperature and time means? So, that is a minimum temperature and minimum time your product needs to receive during processing. And in the case of ohmic heating, again it's the temperature and time as the critical process parameter. Ohmic heating is also a complex process, so you can able to model that using multiple field. So you have an electrical field. During that, you are going to generate certain voltage, so that's your heat generation. Then you have a temperature distribution field here, and from that, I think the details of the models are available in the link shown here. And rather than going into details, I am going to just highlight two results. Let's think about a simple case. You have maybe a 1 feet long small bench scale ohmic heater. So you have ohmic heater and electrode, and let's say this is 1 feet diameter, 1 feet in length, and maybe 1 inch in diameter. And I put some type of solid in here, and then I am going to fill the rest with some heating medium, so water or certain salt solution. What I am interested in the modeling is, I am interested to see how the temperature happens within the solid and within the liquid. So, in the first case, you are processing 150 seconds, your single cylinder particle is 1/3 as conductive as the fluid. So, the fluid is more conductive, so that conducts electric current faster, the solid conducts electric current slow, and you have electrode here, electrode here. So, what happens is, if the solids conduct slow, it's going to be heating slow, showing maybe more green color, showing its less temperature. Whereas this is much hotter, so showing somewhere 115, 116. So, in other words, the current try to flow wherever the electricity allow that to pass. Since the liquid in this case has a higher conductivity, the current try to pass through without passing much in the solid. In the second case, so the first case is a well mixed fluid, so that means you have much more uniform conditions. In the second case, you have static fluid. So, that means you can see here the solids kind of slowly heating, but you are not mixing the fluid. So, that means you are going to have a lot of hot zones in the top, because there is a lot of electric current passing through, whereas here you have less current is passing through. You kind of look at those two scenarios, whereas this is a mixed. So, you can think about, you place the ohmic heater in a table, or you put a ohmic heater in an agitating table. When you put an agitating table, the fluid is well mixed, so you have much more uniform temperature, showing the same color. So, it is around 116, whereas in this case, when you have no agitation, you are going to have more heating in the sections where current can easily pass through. So, that is why it is much harder compared to some section where you have cold spot and so on. So, the point here is, in the ohmic heater, if you have change in electrical conductivity between the liquid and solid, you could have different heating happen in the liquid and solid, and then you are going to have non-uniform temperature distribution. When you have non-uniform temperature distribution, that means that you are not going to heat the entire mass same originally we thought possible. That means you are going to potentially have microbes there. It is probably going to potentially food safety problem. So, in other words, you have to understand how well the electrical conductivity in the liquid and solid mixed uniformly, so that for the current it looks the same mass, whether it is a liquid or solid. If it is the same electrical conductivity, it is going to heat much more uniformly, whereas when the value is different, then they are going to have different temperature distribution. So, the second case is you have single particle. Here this is more conductive, this is less conductive, and then it is well mixed. So, again you can see that it is a much more uniform temperature. Since the product is much more conductive, you can see that product is much hotter compared to the liquid. Whereas, in the case of static system, still product is hotter, but you are going to have cold spot because much lower temperature in this vicinity where there is not much mixing is happening and so on. So, again when you look at some of these advanced processing technologies, you have to look at where is the uniformity of my treatment. If I do not have uniform treatment, where is the location of the least treatment, and then try to understand that. And then you characterize your microbial kill under those conditions, so that you can have estimate to the regulators. So, the principal mechanism for microbial kill with the ohmic heating is primarily heat, and there is no contribution from the electrical heat. So, in other words, I am heating with the ohmic heating, but I am going to assume I am using only 140 C. There is no contribution of electrical field. Whereas, I think more recently researchers trying to include some of the frequency effects and other electrofield effects, see whether there are non-thermal effects of electric field in terms of killing the bacteria. But right now, from a regulatory point of view, you primarily look at only thermal effect during ohmic heating. So, ohmic heating can be processed for number of different type of products like soups, liquid egg, juices, seafood. It can be used for extraction, fermentation. So, interestingly, when you apply electric field under certain conditions, it is going to stimulate the growth of microorganism. So, you can accelerate the fermentation process with ohmic heating. You can also use ohmic heating as a branching step, and there are commercial applications like fruits, sliced fruit, sumi products and so on in the market. So, this is just some of the reading material you may find useful for the purpose. With that, I am going to stop here for some questions.
So, this heating method, is it only suitable for liquid substances?
Ohmic heating?
Yes.
It can.
In the last slide, the examples which you gave, that stew and everything, those were liquid substances. So, can we use this method for solid products also?
You can use it for solids as well as liquids.
Okay.
But I think the idea here is you want to have homogeneous electrical conductivity values. So, when you have liquid and solids, you may have different liquids have a different electrical conductivity value, and solids may have different electrical conductivity value. Controlling them may be a little more challenging. Whereas, if you imagine you have fruit puree, you have much more homogeneous, same electrical conductivity value, you can able to accomplish.
Yes, so that question also I wrote, that how is this uniform heating ensured in ohmic heater in case of heterogeneous food like soup with solid?
So, when you have a heterogeneous fluids, it is much
Yes.
more difficult to demonstrate the heating with the ohmic heating. So, then you have to look at the electrical conductivity product characteristics, and then you have to find the different resistant characteristics, and then relate back to the time and temperature, and then you have to identify the cold spot, all those things. So, the calculations going to be much more complex. It can be done, but it is much more complex.
Okay. Okay, sir.
So, ideally you want to have much more homogeneous electrical conductivity value, so that the current can pass through much more uniformly.
So, sir, is there any alternative for this heterogeneous kind of things?
So, think about we are going to learn different technologies during this advanced processing type of lectures,
Yes.
and each one is a tool. So each has certain benefits, each has some limitations.
Yes.
So that means everything is not going to be uniformly applicable for all the scenarios. So you have to like use different tools wherever it's useful.
Okay, sir. Thank you, sir.
My question is, what kind of products undergo ohmic heating and what kind of products undergo aseptic heating? How is that decided?
Right, sure. So again, as I mentioned, aseptic processing, ohmic heating, these are all two different tools. Both prepared to accomplish the same thing, which is sterilization of the product. Aseptic processing is relatively more conventional thermoprocessing type method, whereas ohmic heating require knowledge of electrical conductivity, all those things. Ohmic heating probably much more useful when you have very, like, for example, you think about dense fruit puree or dense liquid type of material. Pumping through a aseptic processing system, it may be challenging because it has a high viscosity, all those things, and then the heat transfer may be a little bit slow. Whereas ohmic heating doesn't care because it doesn't worry about conduction heat transfer, it worry about the electrical conductivity. So as long as that material has the same electrical conductivity, it will heat quickly. So under those conditions, electrical conductivity probably going to work better, or that product ohmic heating maybe work better. Whereas you have a simple liquid or liquid with solids, aseptic processing may be good under those conditions.
Right, or is it probably the kind of shelf life that they expect of the food product?
No, the shelf life, both, if you properly design, they are going to have a long shelf life similar to whether it's aseptic or ohmic. They are same tools. You know, like if you think about in the kitchen, there may be multiple knives there, but you are not going to use same knife for all the things you want. Maybe different jobs require different knives. The same way, different product categories may require different type of technologies. So in the case of ohmic heating, it works well when you have high viscous product or highly concentrated type product, whereas aseptic may be more liquid with solids or more liquid type products.
Okay, sure. Thank you.
Hello, sir. So my first question is, as we know that many of the industries are working on the conventional heaters. So would it be justifiable to switch on the ohmic heating if they want to switch? Because as we know that in the process involved, there are many insulated materials we want for the ohmic heating. So sir, is there chance that the companies would hesitate with the cost involved in it?
Right. So again, you're going to have different tools, right? Like ohmic heating, aseptic. Later on, we are going to talk about microwave heating. Each has a different principle of operation, different heat transfer mechanisms. And when food processors want to implement, they have to consider the cost, they have to consider the quality, all those things. So they have to choose based on that. So they don't have to use ohmic or microwave or aseptic. Remember, consumer, when they buy product, they are not buying a product, I am buying because it's ohmically heated, or I am buying because it's aseptically heated. They are buying because it's a better quality, taste better, all those things. So the technology is going to stay behind the scene. It's a processor. They are going to look at the economics, what facilities available, what are the things they have, and then they choose which direction they want to go.
Yes, sir. In that context, I want to add, just like sir, we have seen that there are many instances that government and the other regulatory bodies are trying to say that we want to reduce the dependence on the conventional heaters, because pollution is the main concern, or the method which we are using for the heating is main concern. So the government or any regulatory body is coming to us to help the industrialists to for these instances, so that cost would be lesser, or subsidize them on the when they are going to adopt these new technologies.
Right. So again, you are bringing the sustainability dimensions. So if you compare canning has much more emissions because of the heat loss and other things. Aseptic going to be less, whereas if you look at Ohmic heating and other electro-based technologies, because they use electricity, the electricity can be produced using even solar heaters and so on. So there's going to be different dimensions. Now, the food processor, they have to stay in the business to make money, to provide salaries for the people. They need to stay profitable. So they have to look at the big picture. Is this being supported or it's not being supported, and then they make the decision. So in one country where some others have supported, they may be going for Ohmic heating. In other country, maybe they may choose something different because that is not supported.
So my second question is, are we in the position that we can comment on the effect of pH and other material properties such as size of material on the process?
For Ohmic heating?
Yes, sir.
Yeah, so the pH is going to be similar to thermal process. So acidic products going to have much shorter time because because the spores, bacteria doesn't grow well in acidic environment, so they require only mild treatment. So it's kind of similar. What's the other one?
Sir, other one is the material properties such as size of material, if you are talking about the solution.
The size of the material, the diameter of the particle?
Yes, sir.
So if you look at the Ohmic heater, the particle size probably is relatively less important, because in traditional conduction, convection heating, the size is important because how much time it takes to go through the particles. Whereas Ohmic, supposedly the whole thing going to be heating, so then the sizes become less important.
So my third and last question is, if we are talking about the electrical ohmic heating, sir, we know that if we are increasing the distance, there will be increase in the resistance also. Sir, so we can comment that it there not the chance that if you are using at industrial scale, so it may be the chance of over processed or under processed.
Yeah, you have to kind of remember in the one of the first slides I showed multiple electrodes. So you can able to control the heating rates in each section, so that you can see what temperature the product goes through different Ohmic heater, and these can be computer controlled. So that means you may have thermocouples attached with your computer that monitor the process, and then you can able to regulate the passage of electricity to different Ohmic heaters, so you can able to control your process efficiency.
Sir, out of curiosity, sir, as the question was arose that in the heterogeneous mixture, how we can control, sir, could we use the agitator with the process so that the heterogeneity or the problem with the heterogeneous material can be solved?
Yes, I think definitely you can add a agitator of some sort inside a Ohmic heater. Now remember, Ohmic heater itself has, you have a tubular structure and then you have electrodes, and then you are adding an agitator. It's going to add the mechanical complexity of your system. Now whenever you add multiple components, you need to make sure that all those components work in sync. So what if you have a system and the agitator stopped working during the process? Then your assumption may not be valid. So all those things you have to keep in consideration.
Okay, sir. Thank you, sir.
Good morning, sir. Sir, is there any particular compositions for the product which is used in ohmic heating?
Any particular composition?
Compositions of the products.
So the electricity doesn't care the composition. It's just to consider the electrical conductivity. So you may have salt, much higher electrical conductivity, whereas maybe starch or protein may have a different electrical conductivity and so on.
Sir, does nutrient and content get affected by heating any particular product?
So again, ohmic heating or aseptic processing, when you heat rapidly for a short time, the nutrient content is supposed to be preserved. When you have a prolonged heating, that's when you get nutrient damage.
Or sir, any particular storing chamber so as to reduce the reactions between the product and the chambers, storing chambers where we are storing the products?
So you're talking about the electrode and reaction.
Yes, sir.
So you know normally when they have electrodes, when you have for example stainless steel electrode at high temperature, you may have electrolysis. So that's where they may be coating with the platinum coated electrodes, so that it reduce the interaction between the product and the electrode, so it doesn't happen.
So, sir, my question is, in case of like ohmic heating or other non-thermal technology, we increase the temperature, shorter exposure duration we mostly prefer. In case of ohmic heating, pulse electric field as well as CP. So, due to that, we observed that because of this sudden exposure, the proteins or starch molecule, in case of proteins, the active binding site may be explode, or in case of starch, it will be like amylose pectin chain length distribution will be defected. As a result, in final component, what we get, whatever the exposed site of the protein and starch, it will bind together. As a result, it can reduce the bioaccessibility of the nutrients when you consume the human food. So, how to overcome it?
Okay, can you kind of
Okay. So, sir, when you go for the short time treatment, because of that, in certain case protein they expose the hidden binding site for the external parameter. As a result, it can improve the digestibility. In case of starch also, it can depolymerize at a minor scale. But in a negative consequences, if we slightly over process, for example more than 5 seconds, as a result the newly exposed active binding site of the proteins and the depolymerase start will be bind together. In fact, when you consume that, whatever the bioaccessibility the human body should absorb their body, it practically reduce. So, how to overcome this? Because in many processed food item we found the similar consequences.
Right, sure. So this is a very good question. Now, if you look at the research overall done, especially in the US, a lot of the effort primarily focused on food safety. You want to demonstrate the safety, macrobiological safety of the processes, whether it's ohmic heating or high pressure, pulse electric, all those things. The health side of how those processed food affect the health and wellness, I think that studies are only beginning to happen. So yesterday morning there was a discussion about the gut microflora and processed food. Those are things probably we don't have yet. So it's probably going to be the next 10, 20 years, some of those studies needs to happen. Then we will probably have better insights which one of these technologies provide better health benefits compared to the other technologies.
In the industry, when they are doing pasteurization, what is the heating technique that they are using? Is it ohmic heating itself?
What is the heating technique they use in the pasteurization? So normally, at least with the US perspective, they use traditional pasteurization, for example milk and other things. They use a traditional pasteurization. Now, more recently in the last 10-20 years, high pressure pasteurization becoming more common, and it's kind of gaining more attention.
Sure, but what is the heating process that is involved? Is it is it the electrodes that are used, or is it the steam? How is
so
that?
in the case of pasteurization for milk, that is more they use plate heat exchangers. So essentially you take steam and then you heat the milk, your plates, and then transfer the heat to the milk, and that's heat the milk. So it's essentially like steam or hot water.
Okay, okay. So there are two types of milk products. One that can even after pasteurization has to be refrigerated, and there is another carton which can sit outside at room temperature.
Right.
So what is the difference in the processing of those two? One is aseptic, the other one is the regular pasteurization, right?
Right. So remember we talked about the term pasteurization, commercial sterilization. the same concept is applied for milk as well. If you do pasteurization, that means you are inactivating only vegetative bacteria, spores are not inactivated, you keep them in the refrigeration. When you heat the same milk to 140 C instead of 72 C, you are going to expose much higher temperature. Then it is called UHT pasteurization, ultra high temperature pasteurization. The milk becomes self stable and that can be kept in the room temperature.
So why isn't the dairy industry adopting ultra high temperature pasteurization?
So, again this is one of the things going to be, the answer is different for different countries. UHT processing is probably more common I think in India and in Europe, where the refrigeration handling network, all those things is relatively either small or non-existing. So, it is much easier to store the milk in a Tetra Pak container in the room, and then you open it, then you consume it immediately. Whereas, if you look at the US, you have extensive network of refrigeration. Most of the homes have refrigerators. So, that means the consumers, they are primarily interested in preferring the pasteurized milk, but they do not like the burnt flavor of your UHT milk, because like I think they acquire taste, that burnt taste, whereas that does not bother the consumers in India or some other places. It is just how they are kind of accustomed to that. So, in fact, I think there were studies done where they were trying to bring UHT milk and feeding young children the UHT milk, so that when they grow up drinking UHT milk, they acquire the taste, so that they become adapters of UHT milk. So, those type of things, but nevertheless today pasteurization is the predominant technology in the US milk pasteurization industry.
Right, sure. Thank you so much.
So, sir, my last question is, in case of like ohmic heating, the fluid will be go, in case of when you go for the simulation, it will be go for the pipe flow. In certain case, we know that the in middle of the section the velocity will be high, and the edge of the pipe their velocity will be less. As a result, the microbes will be deactivated due to this certain shock of the electrical field and conductivity of protein denaturation. So, during this entire process, so we I read several things that in case of that there is a safety concern, because whatever the instrument we are using, there is a wear and tear in case of when we are going to use the electrical rod where the electrical currents will be passages. So, we already established certain rules already forcefully applied to the instrument. So, is there any kind of practical application or regulatory body is there to check either this condition is fully maintained or not?
So, again it probably depends on country to country. So, in the US ohmic heating is not at the moment very broadly commercially used, but they normally check the what they call the electrode. From a Food and Drug Administration, their primary goal is to see what type of things you are adding or removing in the food. So, that is why they are worried about this. Whereas, if you look at the wire connections, electrical connections, all those things, it may be maybe for example, there are government agencies which deals with the worker safety, all those things, they may be kind of follow up on those type of issues.
Okay. Sir, in case of like if you want to formulate the like heat transfer rate or mass transfer flow, mostly we are using as of now, we mostly use the COMSOL software that is too complex. Is there any simple software that can be industrial scale or optimize model fitting software is still exist that we can use, because of that we can collect the data, simply fit the data, we will get the temperature profile distribution?
Yeah, again unfortunately some of those flow field, electric field, coupling and distribution, all those things, it is a complex. There are COMSOL is one example, you have Fluent, there are finite element softwares and other things available, but someone needs to learn and kind of practice them. And I think other thing is probably if you make them too simple for the end user, people may probably make mistakes by not following some of the physics concepts, and that can be potentially problematic too. So at least I am not aware of any simpler software for some of these applications.
Okay, sir. Thank you.